Okay, so go Bears, yeah. Okay, so yeah. Okay, if the periods indicate good, which is the best station here? Which is the best station? KCBS, right? Okay, which is the best station now? Okay, well, I already told you. But if I hadn't shown you, what would the best station be? Would you know? How would you know? Okay. Now, which one's the best station? Okay, now which one's the best station? I don't know. Which one's the best station? Which one? Which one? Which one? Which one? Which one? Oh, okay, at the end I know. Right? Like if I had picked KCBS, I would be very happy at the end. If I had picked Quran, I would be very unhappy. Right? Does that make sense? But it's a little ridiculous for me to ask you to pick before, or even as you go, right? Well, that's what we're going to do today. We're going to tell you to pick the best station every day, and we're going to prove that you're going to do pretty well. You're going to actually find KCBS in some sense. Okay? That's what we're going to do today. Okay? So this is the multiplicative weights algorithm, and the framework is you have n experts. Here are the experts on the first slide were the stations. Right? And they're telling you something. I don't know what I'll give you a better example in a minute, like the weathermen. Each expert may tell you whether it rains or not every day. Right? And so you want to pick whatever you want to figure out whether you want to take your umbrella. Okay? So now we're going to talk about this framework where there's one of the stations is perfect. It tells you the proper thing every day. Okay? And we're going to show that, you can only make a mistake. We're going to give you an algorithm where you can only make a mistake a few times if there's n experts. Log n times, which is really a lot smaller than, for example, the number of experts. Right? This is a little shocking. And now we're going to tell you, and in fact, we're going to then do an analysis that actually does a little better. And it says that instead the best expert makes m mistakes. Now, can you get close to m? On making only m mistakes. And what this says is, well, I'm going to give you a strategy that it does. Let's say the epsilon is small in the first thing. 2 times 1, let's say epsilon is small. Twice as many mistakes as little m. Only twice as many mistakes as the best expert. Okay, I'm going to give you an algorithm that every day you do something and you figure out whether it rains or shines, and you're only going to be wrong twice as often as the best person, the best predictor. Plus this additive term. And you see the little trade-off there with the epsilon. If epsilon goes to 0, the additive term goes up big, but the multiplicative term gets small. And then we're going to show you another strategy that gets rid of this factor of 2 in terms of the multiplicative term. In fact, so this other strategy will give you. We're going to talk about losses instead of mistakes, but it's just a slight generalization. And here we're going to get rid of this factor of 2 in front. So we're going to do very close to the best expert multiplicatively, and then sort of close additively. This log n over epsilon hopefully goes to 0 as this process goes on for long enough. Okay? And the strategy is we're going to choose experts proportional to weights, and the weights are going to be proportional to this loss. If you lose, if you predict incorrectly, we're going to penalize experts. We're going to tell the experts, you're terrible. I hate you. But we're not going to tell them, I hate you very much. We're just going to say, I hate you a little bit, 1 minus epsilon. So, and then we're going to say, and if that expert loses a lot, this number is actually going to get very small. So the big losers are losers, right? We're not going to pick the losers. Okay? So, and this algorithm appears in many frameworks. So we're going to next on Friday we'll show you how to prove strong duality of 2-person games. I should tell you where did 2-person games go. I'm going to record it. I recorded one. It sucked. So I'm going to record another one. So I'll record it after tonight. Yeah, I had trouble with everything when I did the first one. I have trouble with my whole life. Okay, so but I'll try to do better, and I'll record it and post it this evening. Okay? Okay, so, this is what you want to do. Which stock do you buy? Which weather station is most accurate? Which road do you take every day? These are choices you make every day. How should I behave? Today, I should do what seems to work. That's sort of what the multiplicative weights framework really does, but I shouldn't do it too harshly. I shouldn't just say, oh, that didn't work yesterday, let me go the other way. I should say, well, over time, that one sort of worked about this well, and sort of judge along there, okay? And avoid a little what doesn't work. If you get burned once, you don't quit that route, you just sort of back off a little bit, okay? That's the idea. Do something a little more that does work, right? So that's the idea. This is what you do in life, maybe. You don't, like if somebody disappoints you once, you don't write them off. But if they disappoint you every day, okay, that's enough with that person, right? So, and so the point is, this is maybe an analysis for that working, okay, if you like. And it's very natural strategy, and understanding the framework in which that natural strategy works is maybe one way to view this. So every day, experts, so expert 1, it rained, shine, right? And this is what the experts are telling you, and this would actually happen. Okay, the first day, who's right in this scheme? 3. Hi, Matthew. This one, who's right? 2. You notice something about 3 and 2? They don't really do much. They just predict. 2 always says it's sunny. Yay. 3 says it's rainy. Okay, so which advice do you follow? So the idea is generally you tend to follow who's correct most often, sort of. And the question is, how well do you do in these settings? Or even how do you define doing well, right? If all the experts are terrible, there's nothing you can do, right? If you follow any of these people's advice, it's terrible. Okay, so we have to decide what it means. So let's set this up so that, in fact, there is a very good expert. There's one expert who's great, never makes a mistake. Okay? What's your strategy? You choose any expert that has not made a mistake. That seems obvious, right? You know that if somebody made a mistake, they're not perfect, so they're not the perfect expert. I already told you there's a perfect expert. Once somebody makes a mistake, you just cross them off your list forever, right? They're not the perfect expert in this setting. How long to find a perfect expert? Well, maybe never. Right? You may never find the perfect expert because maybe they're all, maybe you never see a mistake. Right? So in some sense, maybe they're all perfect. I mean, it's sort of a little weird, right? The whole question is, can you find the perfect expert? It's not even well posed. Okay? So what's the model of success in this world? The model of success is how many mistakes could you make? If every day it's all perfect, you never make a mistake, you're perfectly happy. Right? You pick one expert and you follow them and they're perfect, and that's sort of okay. So we're going to do the model for analyzing this thing is a mistake bound. How many mistakes do you make? Okay? So now we have an algorithm. You choose any expert that has not made a mistake. This is this third line here, which I should have put in blue, but it's the third line. Choose any expert that has not made a mistake. So this tells you the answer. So how many mistakes would you make if the adversary does this? So here, what is an adversary here? The adversary just wants to make you make as many mistakes as possible, even though there's a perfect expert. So how does the adversary do that? Say they watch what you choose. They see, oh, you choose that guy. Aha, that guy made a mistake. Okay. And then you choose a different guy because you're not going to choose that guy anymore. He's not perfect. So you choose a different guy, and the adversary makes that guy make a mistake. Okay, disaster, right? So what is the number you get here? Yeah, because there's one perfect expert, and he gets to decide later which one's the perfect expert. Okay, it's hidden from you, just like on that first slide where the SHs and all those things should have been hidden from you. Okay? So n minus 1. Not n minus 1 factorial, n minus 1. Okay, so, sorry. I'm a little punchy. Okay, so regret. Well, the adversary makes you want to look bad. Okay? It's very self-referential. Okay, well, I don't know what to do here. Okay, so you could have done so well. You see, there was this perfect guy. You never had to make a mistake, but you didn't. Ha, ha, ha. That's what the adversary is trying to do. Make you feel bad about yourself, right? Maybe some people would call that Berkeley, but I would disagree. So, okay, so analysis of algorithms. You want to do as well as possible. So in this model, you want to minimize your regret. Okay? Regret is a difference between what the best expert does and what you actually did in your decision making. Okay? So in the previous model, what it was, the best expert made 0 mistakes, and you only you made n-1, right? Which is kind of bad. You look pretty bad at that point. Maybe that's bad. Maybe you can't do better. I don't know. I do know because I know what's on the next slide. So we have an algorithm. So now here, this is an analysis of an algorithm. We have an algorithm. The algorithm is choose one of the perfect experts. And we saw the analysis is it makes you look bad, this bad. n-1 mistakes where you could have done 0. Right? So you have n-1 regret compared to the best expert. Okay, and we had a lower bound. So we showed you that you can't do better, and you obviously can't do much worse, right? You would always switch your experts, so we could also do the upper bound. Okay? Every mistake finds a fallible expert. You throw them out, and in the end, you do actually find a perfect expert, if there are n-1 mistakes. Is there a better algorithm? What do you think? Of course, there's a better algorithm. I'm telling you, there's a better algorithm. But what do you? Just think about it for a second. What do you think it is? Okay. What you might be. You have a lot of experts, right? You can sort of just take a majority of what they tell you. Right? You're making a decision. You're not trying to find, you're not trying to find your. What are those things? Cult. You're not trying to find a cult leader. You're trying to make a decision, and you get to see all of their inputs. So you might as well just take the majority. Try to go with the majority of previously correct experts. Anybody who's not correct, you throw them out. Everybody else, you say, well, that could be the perfect one. Let me just take the majority of whatever they say. Okay? There's rain or shine. You take the majority and you go with that decision. Okay, this is pretty much what you would do anyway. If you have a lot of input, maybe you would vote, have people vote, right? This is democracy in the sense that after you send a few people to prison. So that's a Putin joke. So I don't like Putin. I apologize to anybody who does. But how many mistakes could you make in this model? Yeah, you can make at most log n. So we get like exponentially better doing this. Okay, so that's pretty nice, right? So the idea is when an algorithm makes a mistake, this is the size. I'm using the size and words in the middle. The number of public experts drops by a factor of 2, right? So since the number of experts, perfect experts, drops by a factor of 2, these are people who never made a mistake, right? Why is the number of perfect experts drop by a factor of 2? Because at least half of them told you the wrong thing. Okay? That's why you made a mistake. So you get to throw out half of them. So the number that are left is at most half of them. Right? At least half of them were wrong, and you went with all these wrong guys, and then you said, oh, I'm done with you. Okay? Okay, initially there's n perfect experts. After one mistake, at most, n minus n over 2 perfect expert. After 2 mistakes, it's n over 4 perfect experts, and so on. Okay? And so now finally, how many steps does this take? Yeah, now we love our logs. We know our condition was we have at least one perfect expert. So we can't ever get below this. So after log n iterations, you won't. After log n mistakes, you won't get any fewer. You won't make any more mistakes. So at most, I'll have log n mistakes, right? Pretty cute, right? Nice. Okay, what's the goal? So do as well as the best expert. So what do you think the algorithm is? Yeah, right? Yeah. Very good. Okay, so that's what we're going to do. Okay, he said don't take him seriously. We're all doing this in words instead of math, and I think that's fine. He says take the experts less seriously when they make a mistake. Okay, so there's not really a majority here, right? Because, who's the majority? Some of them made some mistakes, others made different amounts of mistakes. And what he's saying is sort of weight them by their mistakes. Okay, that's what he's basically saying. So you penalize inaccurate experts. Okay, so the best expert is penalized the least. That's sort of the intuition, right? So initially, you think of all of them. We're going to go with some sort of weighted majority. So we're going to give all of them weights, and in terms of that sort of indicates how much we trust them. Okay, we say at the beginning we have no information. We trust everybody equally, and then we predict with the weighted majority of experts with these weights. So initially, the weights are all uniform, so it's just the majority. If somebody's wrong, you divide their weight by 2, meaning that they go down in your judgment. Okay, so they get less impact on your final decision. Okay, that's the algorithm. Okay, so this is the algorithm. So let's do the analysis. Okay, so the goal is the best expert makes m mistakes. Let me see what my timing is. Sorry, I'm going to turn this do not disturb. Okay. The best expert makes m mistakes. Okay, that's the idea. So we're assuming something, and we want to do something close to that, close to m. Our algorithm, this algorithm here, we're going to make mistakes. If we're wrong, we're going to make some mistakes, right? Okay, so we're going to do a potential function again. This is much like we did last time, right? What the progress we made in the perfect expert case is if we made a mistake, we knew half of them were wrong. So we throw them out. So we make progress. We only have to listen to fewer people. Okay. So we're going to take a potential function, right? This sum of the weights, because the weights are only going down. So that's a good potential function because it does only one thing. It doesn't go up and down. It just goes in one direction. It sort of reduces over time. Okay? And it's initially n, right? The sum of the original weights is n. For the best expert, b, the weight is always greater than 1 over 2 to the little m. Right? Because you only make little m mistakes. And the weight was initially 1, and you will only multiply it by half little m times. Right? So this line here kicks in for the best expert. The best expert only makes little m mistakes. So the total weight of WB is 1 over 2 to the m. Okay, so what does that tell you? That tells you the potential function doesn't get too small. Right? So we have a potential function, the sum over I of WI. It's a potential function. It decreases because we're only decreasing the WIs. But we only decrease WIs if a lot of people are wrong. Okay? So now the best expert is at least something. And the best expert is in this sum. So this sum doesn't get too small. So that's the idea. This the potential function decreases when people are wrong, and this potential function doesn't get too small. Okay? Already. That's what we said for the best expert. Now for each mistake by the algorithm, the total weight of incorrect experts is reduced by, what do you think, -1, -2, a factor of a half? What do you think? What did I say? Okay. Okay, well, yeah. Okay, I told you the answer. You can read. That's good. Okay. Each incorrect expert weight is multiplied by 1/2, right? So we don't know. So none of those 3 answers are correct, actually. So that was just mean. But each incorrect expert's weight is multiplied by 1/2. Okay? This is a little subtle. So you gotta pay attention here. Okay? So what's the total weight of incorrect experts is reduced by a factor of 1/2. That's what I'm saying. So it's the third one. That's because each incorrect expert's weight is multiplied by 1/2. So all the weight of the incorrect expert is multiplied by 1/2. Okay? So the total weight of these incorrect experts is reduced by 1/2. Now, when you made a mistake, what is the total weight of the incorrect expert? Well, it's at least half of all your weight. Right? Because you made a mistake and you use a weighted majority. Okay? So that says at least the total, half your total weight is doing the wrong thing. And all those people who do the wrong thing, they get punished. Their weights get put down by a half. Okay? So the total weight, which is this potential function, the sum over I of Wi, it's the total weight of all experts, including the good experts. Okay? And that decreases by a factor of a half or a factor of 3/4. Okay, so it's not a half, right? Because you're only multiplying the incorrect experts by a half. But the incorrect experts is at least half of them. So you lose at least 1/4 of your weight, right? So that means the mistake means greater than half the weight with incorrect experts. So it's 1/2 the total, greater than 1/2 the total because you made a mistake. That's what mistake means, right? Half your weight is wrong. And each one of all the weight that's wrong is multiplied by half. So the reduction is at least 1/4. Okay, that's how much your weight reduced by. Okay. Okay. So the 13 is there for mysterious reasons. Yeah. It was supposed to turn this thing blue, but it got out of the code and got it into the text. So what this says is how much the weight gets reduced by the sum of these weights, the potential function, which is just the sum of the weights, is decreased by a factor of 3/4 when you make a mistake. Okay? When you don't make a mistake, you don't care. The weight didn't decrease or not. Something happens. Maybe the weight decreased. Maybe some people made mistakes, and you still decrease the weight. Okay? So what we have is that the sum, this potential function, is at least the weight of the best expert, which doesn't make too many mistakes ever. Right? That's 1/2 to the m. And the sum of the weights is less than, every time you make a mistake, m is the number of mistakes by the algorithm. Every time the algorithm makes a mistake, you multiply the total weight by 3/4. And the total weight initially was n. Right? The sum of the weights at the beginning was n. So we have this formula. Right? And what we wanted to do is say, how many mistakes does the algorithm make? So we want to compare, this is the algorithm. It's making m mistakes, right? The algorithm, big M mistakes. And here's the best expert, it makes little m. So I want to bound the number of mistakes, big M, by something with little m. And we know we have one now. If you just cover this up, right? If you cover this up, m is a big M mistakes. The algorithm makes big M. The best expert makes little m. We have this inequality. We can get rid of the thing in the middle, right? That's the way inequalities work. And now we want to sort of get an upper bound on big M. So we have to solve this, right? These things are in the exponents. So the obvious thing to do is to take logs, right? You get minus m is less than or equal to big M minus big M times log of 4/3, right? Where does the minus come from? The minus comes from the fact that we're taking log base 2, right? But this is 1/2. So that's why you get a negative. Okay? Does that make sense? Like when we take log base 2 of 1/2 to the m, that's 2 to the minus m. So log base 2 of 2 to the minus m is minus m. Okay, that's what this left-hand side. Similarly, this is what happens here. I flipped the base. Okay? Now we can just solve. Right, it's a little weird because this is bigger, but you're taking something less than 1, it's sort of, this is how it works. It seems like it's weird because big M is on the side with the greater than, but there's a negative because you're multiplying by something less than 1. Okay? Okay, so then you can solve. There you go. So it says the number of mistakes you make using this weighted majority algorithm is at most 2.4 times the best expert's number of mistakes, plus a little bit. Okay, and that log n is there for a similar reason as the perfect experts. Okay? Is that clear? Okay, so now can we do better? That was one algorithm, and we have this weird 2.4 there. Can we drive this down to something really small? Okay? We'd like to, for example, could we drive it down to 1 here? Okay, so we could have multiplied by 1 minus epsilon for incorrect experts, and now you get 1 minus epsilon to the m. The best expert, its weight is at least 1 minus epsilon to the m, And we can do this analysis again and to see that half the weight is multiplied by 1 minus epsilon. And so you get something like this. And you massage, you massage, you massage, and you massage, and you massage, and you massage. So you're just taking logs of both sides. You do a rule of logs. You're taking these little m down and big M down here. You're taking the product. You're making it an addition. This next thing is using this formula is used here. It's just you can do this with the Taylor's expansion of ln of 1 minus x. You can see this from a Taylor's expansion. Okay? Okay, so it's just a bit of massaging, and you can do it. And so what you get is that big M is less than 2 times 1 plus epsilon times little m plus 2 ln n over epsilon. Okay? So as you drive the epsilon down, you're making fewer and fewer mistakes as a multiplicative factor of m, and you make some more mistakes with respect to the ln. Okay? Okay. So it approaches a factor of 2 of the best expert performance as m goes to infinity. Okay? So, if you sort of think of this as sort of a small order term, and you see that m, over time, everybody makes mistakes, and you collect them. So if this is going to infinity, you only do twice as many mistakes as the best expert. Okay? Okay. Is that the best analysis? Okay, let's think of, can we do better? Is this factor of 2 necessary? Can we really get something like this? That would be nice, right? You sort of do almost as well as the best expert in this case where you go into infinity. Okay, so let's consider 2 experts. A is correct on even days, and B is correct on odd days. So the best expert performance, it makes either both of these experts, expert A and expert B, get it right half the time over the long haul, over T steps, where you do this for capital T steps. Okay, and the pattern is, but what happens is you're going to go whoever was good last time, whoever made a mistake last time, you're going to move away from them. So every day you're going to make a mistake if you sort of start out wrong. Okay? So every day you make a mistake, or T minus 1 mistakes. Okay, so it's almost a factor of 2 worse. Right? So this factor of 2 is inherent. You can't do better with this algorithm. Okay? It just says we have 2 experts. Alternately, they're right, so each one is right half the time. But since we're doing weighted majority, one of them is going to have a little better weight, and it's the one that's going to be wrong today. Okay? Because that guy's a little behind. Okay? Okay, so now is there a better approach here? Yeah, I don't know. Okay. So we should use randomization. See, this says it's excited, right? The title gets all these exclamation points. So you choose the expert I instead of like taking the weighted majority. We're going to just pick expert I proportional and just listen to what they say. Okay? And we're going to pick them with probability proportional to the weight. Again, we're going to have the same notion where all the experts have a weight, and now we're going to pick each expert with weight, with proportional to its weight, and do whatever they say. I mean, this is also a nicer algorithm, because now the experts don't need to tell you just one of 2 things. The experts can tell you to buy Google, or buy Amazon, or buy this, right? So in some sense, this is even a better algorithm, right? In some sense, you're just listening to one person, but what you're doing is you're picking the person you listen to that day from a distribution, from the weighted distribution. Okay, so the bad example says, after a while, A and B have nearly the same number of mistakes, so each one will have about the same weight. So in this case, you'll choose each with approximately the same probability, and each is right about half the time. So you have a 50% chance of getting it right every day after some initial period. Okay? So the best expert makes T over 2 mistakes, and that's what we get. So we do about the same as the best expert. Okay? So this already helps this bad example. Instead of us doing twice as bad, we do about the same as the best expert. The best expert gets it right about half the time, and this algorithm also gets it right about half the time. So already it's an improvement for our bad example. So if we want to say an algorithm is better, it better be better on the examples we know our other algorithm is bad on. All right? And so, okay, here's some formulas. Okay, so there's some epsilons, and we can do this one. This is a good one. 1 minus epsilon to the x is less than or equal to 1 minus epsilon times x. This comes from, there's a number of ways to prove it. You can use calculus. You can look at the graph of e to the x. That also shows you. Okay, and this is, again, you can use Taylor's formula, and you can get these inequalities. So we'll use these inequalities. Okay? So the proof idea is here is this Taylor's formula. Is Taylor's formula for 1 minus x. Okay, so it's very useful to sort of, this is nasty. This is nice, right? Epsilon. It's a very simple function of epsilon here. Okay? This is sort of in between nasty and nice, right? That's just like, I don't understand logs. Okay? So, okay, so now we're going to change our model. Now we're going to say each expert can have its own loss. It's not about mistakes. Each expert gets assigned a loss. Whatever they tell you, you don't care what they tell you. You care what it cost you. Okay? So here the costs are between 0 and 1. And again, you're thinking you only lose. Okay, I don't know. This is a pessimistic lecture. But you want to minimize how much you lose. Okay? So, so L sub I t is the loss of expert I on day t. Okay, that's what that says. Okay, and that's just you don't know them until afterwards, after day t. Okay, so initially you have we start everybody off equally. We choose an expert I with probability proportional to Wi, and here big W is the sum of the weights. And when somebody makes a mistake on that day, or somebody makes some partial mistake, these LITs may be in the interval between 0 and 1. We multiply that weight by 1 minus epsilon Li to the t. So even if LIT is a half, you can still, that's something you put into your computer or your calculator. Okay? So now I'm going to say WT, this again is going to be our potential function, is the sum of the weights at time t. Okay? So W0 is n, right? It's the sum of the weights on day 1. Okay, so now the best expert, B, loses L star total. So you know at the end of time, the total weight, the sum of the weights is at least the weight of our best expert, which is at least 1 minus epsilon times L star, where L star is the total loss, right? Because every time you multiply by 1 plus 1 minus epsilon to the L1t, 1 minus epsilon to the L2t, L1, let's LB1, and then LB2. So when you multiply a bunch of things together, the exponents add, right? A to the x plus a to the y is a to the x plus y. Okay? Okay, so that's all we're doing. We're saying every time you multiply this weight by something, you're going to accumulate, basically by the end, this 1 minus epsilon, it will be at least 1 minus epsilon to the total loss. It'll be equal to the 1 minus epsilon to the total loss, in fact. Okay? Now, what does the algorithm do? The algorithm loses or not. It's randomized, right? And so your loss is, since you're picking randomly with weight Wi, you have some expected loss. That's the way to evaluate the algorithm. What's your average loss? Okay? So the average loss is, well, you're picking expert I with probability Wi over W. Wi over the total weight. And that's what this probability is. Wi over the total weight. I should have not put the Li in the exponent. On the fraction. So the probability you pick expert I is Wi times over W. And the loss you get for expert I is L sub I to the t. Okay? So this is your expected loss. The algorithm's expected loss. Okay? Does that make sense? Just using all the formulas, all the notation. It says you sum over all this is, just if the formula bothers you, you're summing over all the possible experts of the probability you choose that expert times the loss of that expert. Okay? I mean, you don't know it until the day after, but you can write it down as an analysis when you're doing the analysis, which is what we're doing. Okay, so for epsilon less than or equal to half, Wt plus 1 is less than or equal to Wt times 1 minus epsilon times this expected loss. So what this says is if you have a big expected loss on day t, this weight goes down fast. Okay? That's exactly what you're saying. And if you have a small expected loss, then this weight doesn't go down so fast. Okay? So, and now we're saying that the weight, and this first one, remember, it's just like the perfect experts, or the majority, weighted majority. We know the weight doesn't get too small. So if large loss drives down the weight. So it says you can't have too large of a loss because the weight can't get too small. Okay? Loss is weight loss.
Weight loss.
Okay. Okay, so let's see. What are we doing? The weight t plus 1, let's call the wi, is the weight at time t. What happens is you sum over the experts, and each expert, you multiply its weight by 1 minus epsilon for the loss on that day. Okay, that's just what the algorithm says on step 3 there. So every weight, the weight on t plus 1 is the weight at t times the 1 minus epsilon to the loss on day t. That's how the weight is changing. Okay, this is just from the algorithm. Okay, now that's less than this thing because the previous slide says 1 minus epsilon to this thing is less than 1 minus epsilon lit. You can get this also. You can see this in the graph. This is a linear function. It says the tangent line at 0 is bigger than this. Okay. Okay, so because it's negative, it's lower than it, or it's bigger than it. Okay, so now what I do, this is just multiplying through. There's nothing interesting here. I mean, there's something interesting here. I don't know. Okay, you multiply by this, and you multiply by this. This thing is the sum of the 1 times wi's. This is I'm just putting this in the middle and putting a summation. Right? It's just algebra. Okay. Now, this is nice, right? But this is good because this is a potential function, right? The sum of wi. Okay. So let's factor that out. I'll factor out the sum of, I multiplied through, and now I factored out the sum of wi. And I have sum of wi here, but I really, this thing is all hooked together, so I have to just put it underneath. So it's a little bit silly. Okay? So I factored out the sum of wi. Okay. What do I do now? What is this? Do we see this somewhere on the slide? Yeah, this is also the expected loss. Right? So this is what we're saying, right? We're trying to write how much does the weight drop in terms of the expected loss. Well, here's the expected loss. Right? That's the proof. Right? Okay. Okay, so when you have a big loss, the weight goes down fast, yet the weight can't get too small. Okay? So you can't have too big of a loss. That's, again, the intuition. Okay, here's this analysis. That's a big pie where you're multiplying all the losses of all the things, all the days. You want to take logs, right? This is something. You take logs. That's just taking logs, and you take logs of both sides. You get the L star comes out front. I'm just going to talk about the left-hand side. The L star comes out up front, and then you have an ln of 1 minus epsilon. The right-hand side, the ln and n comes out because you're multiplying n times this product. The product turns it into the sum of these ln 1 minus epsilon LTs. Okay? The log of a product is the sum of the logs. Okay, and now we use this formula again, and that's what we get. And now we're trying, just to remember, now we have a very nice thing. When we use this formula, this is nasty. We're trying to get a bound on the sum of the total loss. Well, there's the sum of the total loss. That's why I use this approximation with ln 1 minus epsilon is less than or equal to minus epsilon. Then I can simplify this. And then that sum just goes in to the sum of the loss. Now we could solve, and we get the sum of the total loss is less than 1 plus epsilon L star plus ln over epsilon. Okay? Just some algebra. Okay, that's the total expected loss of the algorithm, and it's within 1 plus epsilon-ish of the best expert. Right? We're basically losing, the best expert does this, we do almost as well. I mean, if you sort of assume this is a little small. Right? There's no factor of 2 here, right? This is very nice. It's also more general, because you can listen to an expert if they give you, you don't need only 2 sorts of advice. Okay, so why are we being so negative? You can do all this where each day, each expert gives you a gain in 0, 1. Then if somebody gives you money, you raise his weight, and so on. You can do all this stuff, and blah, 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 and you can do all kinds of stuff. If you're not in 0, 1, say your losses are in the range 0 to rho, you pay additionally here, right? And the reason you have to pay in the additive term is rho could be very large, and so it takes time for you to average out your loss. One day, the first day, you don't know anything, and so you pick somebody and you lose big. So you have to have an additive term, okay? And if you don't switch your idea, you can get that additive term for a while. If you don't switch, somebody can be bad for a while, and you keep picking them, and that's why if you don't move quickly, the additive term may hurt you, and that's what the epsilon is here. But if you move slowly, you get the benefit that the multiplicative factor is smaller. Okay. Oh. Okay, so what if you only know the expert that you picked? Like you decide to drive on this road, and it was terrible today. I mean, this example makes no sense anymore with Google Maps, but okay, but I'm old. Okay, forgive me my age. So you knew it was bad yesterday, so that's all you knew. You didn't know what the other one was. Okay? So that's called the bandit problem. This is it's called the bandit problem because you're in Las Vegas and you want to see which arm to pull. Right? There's many arms on these bandits, and one of them, they like to make the gamblers think they actually are doing something, so they have several arms, and they want to see which arm gives the biggest payoff on average. And you only get to know the payoff when you pull the arm. Right? Okay? So, it's a model for studying exploration and exploitation. Okay? So this is what reinforcement learning is. Like a little robot is exploring the world, and it dies. That's bad. It learns not to do that anymore. And then the next day it explores it doesn't do that, right? Or does it again because it's only multiplying by 1 minus epsilon. And so, but this is actually how it works. So you get reward for, you have a slew of actions you can take, and you pick, the experts are just a set of actions. Okay? You don't know anything about that. So this is the other one. So these are algorithms for that. Now you have to not only decide which expert to choose, you also have to decide which ones to explore, because maybe there's some good expert. Maybe you're doing well, but maybe you also want to explore somebody else because maybe they do better. Okay? Okay. So you can minimize a convex function on R to the n. X star, there's some expert. Now this is fancy. There's some expert, which is some vector, which minimizes this function. And the gradients are sort of the loss on the experts correspond to the coordinates xi. Okay? So linear combination of the gradients is a linear lower bound on f of x, right? That's if it's a convex function. So it turns out the experts say the average value of the loss is low relative to this lower bound, right? This linear combination of gradients this linear combination is like expected. Expectation is a linear combination of your losses. So this linear combination of the gradients, which gives you sort of a bound on a lower bound on a convex function, gives you something. So, and now it says the average difference from whatever you're choosing on average and the expert is low. The best point in your space, which is the best expert in your space, is low. Okay? So it's sort of a version of gradient descent, but it works with just local gradients. So it's online. Okay, so this was lecture in a minute, and I'm gonna wrap up and let you go. I'll see you on Friday.
discussing the previous predictions, are we assuming that there's no underlying pattern? Like, we're always considering the worst case scenario. But in the bandit problems, it's like, if we're going to do learning, there has to be
Good question.